Hey everyone, and welcome to this explainer. So, have you ever wondered how the absolute smartest engineers, scientists, and inventors tackle challenges that seem totally impossible? Well, spoiler alert, they don't have magic brains. They just have a secret framework. It's basically a mental superpower, and it's called computational thinking. Today we're going to unlock this superpower together so you can start using it in your own everyday life.
Man, we have absolutely all been there. You're staring down this huge, messy challenge. Maybe it's a giant end-of-year science project, or you're trying to organize a surprise party for your best friend. Or maybe you're just trying to figure out how to clean a bedroom that looks like a literal tornado hit it. It feels completely overwhelming, right? You don't even know where to start, so your brain just kind of freezes.
But what if you could hack your brain to just see right through all that chaos? Well, that's exactly what computational thinking is. It's the ultimate tool that top problem solvers use to take a giant, terrifying mountain of a problem and turn it into a simple, easy flight of stairs. It's a life hack that trains your brain to process challenges the exact same way a supercomputer would. Just step by clear step.
To get you thinking like a genius, we're going to walk through 5 quick steps today. Number 1, the problem-solving superpower. 2, the 4 key pillars. 3, designing the perfect algorithm. 4, logic, rules, and loops. And 5, flowcharts, mapping your solution. And fun fact, just breaking this explainer down into these 5 easy sections is actually a real-world example of what we call decomposition.
Okay, let's jump right into section 1, the problem-solving superpower.
So, what does computational thinking actually mean when we aren't talking about motherboards and microchips? Well, if you look at how it all overlaps, you've got computing on one side, computer science on the other, and sitting right there in the middle is computational thinking. See, this isn't just about coding or staring at a glowing green screen. It's really a bridge. It's a set of problem-solving skills that let us take a really complex problem, understand it, and then present the solutions in a way that a computer or even just another human can easily follow. It's all about combining your natural human logic with the amazing efficiency of computer science.
Moving right along to section 2, the 4 key pillars. To actually use this superpower, you need a toolkit, and computational thinking stands on 4 foundational techniques, or pillars. Pillar number 1 is decomposition. This just means breaking a massive task down into smaller, bite-sized parts. Because if you break a huge problem into mini problems, they're suddenly super easy to solve. Think about hosting a giant holiday dinner. You don't just walk into the kitchen and shout, "Make dinner," right? You break it down. You pick a menu, you ask people for help, you hand out specific tasks like, "Hey, you bring the drinks," and you set a time to eat. By knocking out those tiny pieces one by one, that giant dinner practically makes itself.
Pillar number 2 is pattern recognition. This is all about looking at the mess in front of you and seeing if past solutions can apply to it. For example, say you're playing a brand new video game. You might notice some objects or actions that look exactly like an older game you used to play. Because you recognize that this new boss moves just like an old boss, you already know you need to dodge left and jump. Spotting those similarities makes solving new problems so much faster.
Our third pillar is abstraction. If you look at how all those highly detailed cars can be grouped up simply as a wheeled vehicle and then just a generic vehicle, that's abstraction in action. It helps us find the details that actually matter for solving our problem and totally ignore the noise. Like if you're trying to figure out how to transport heavy boxes across town, you just need a generic wheeled vehicle. You really don't need to stress over the car's paint color or what radio station is playing or what type of headlights it has. You just filter out the fluff.
And the fourth and final pillar is algorithm design. Once you've broken the problem down, spotted the patterns, and filtered out the noise, you need a game plan. An algorithm is just a set of instructions for getting a task done. It's literally your final blueprint. Put simply, it's a sequence of steps that a human or a computer can follow to get to the right answer.
Which brings us nicely to section 3, designing the perfect algorithm. Knowing how to actually build that blueprint is absolutely crucial, because if your instructions are confusing, your solution is going to fail. A truly great algorithm follows some very specific rules. First off, it has to be clear and unambiguous, meaning every single step has only one possible meaning, no guessing. Second, it needs well-defined inputs and outputs. You have to know exactly what you're starting with, like the ingredients for a cake, and exactly what you expect to get at the end, a baked cake. Third, it must be finite. This is a big one. The algorithm actually has to end after a specific amount of time. And finally, it has to be feasible. Basically, it has to be practical enough that you can actually pull it off with the resources you have.
All right, section 4, logic, rules, and loops.
Let's dive into the actual nuts and bolts of how these algorithms make decisions.
Real-world logic flows in three main ways. First up is a sequence structure. This is super simple, just doing things in a straight line, executing steps in the exact order they're written. Second is selection. This is where the algorithm hits a fork in the road and makes a choice using an if-then-else condition. Like, if it is raining outside, then bring an umbrella, else wear sunglasses. Makes sense, right? And third is iteration. These are loops, where a sequence of instructions is executed over and over again.
Now, when we talk about loops, there is a massive distinction we have to make. We've got finite loops versus infinite loops. A finite loop is what you'll use most of the time. It has a clear, explicit end. It runs a set number of times and then stops when a certain condition is met. But an infinite loop, that has no explicit end at all. It just runs forever because its condition always stays true. A really great example of this is the repeat forever block in the programming language Scratch. If you use that, your character will just keep doing its action endlessly on the screen until you physically hit the stop button.
And finally, Section 5, Flowcharts, mapping your solution.
So you've got all this brilliant logic floating around in your head. How do you actually share it with anyone else? Well, a flowchart is a pictorial representation of an algorithm. It is basically a treasure map for your logic. And these standard symbols are universal. Ovals always show the start or stop point. Rectangles are used for an action or a process you're doing. Parallelograms show your inputs or outputs. And those diamonds? Those are your decision points. That is exactly where your if-then selections happen. And of course, arrows link the whole thing together so you know which way to go.
We actually use these symbols for totally normal, everyday stuff. Just look at this flowchart for polishing a shoe. We hit our start oval, then an arrow points down to a rectangle. Open the shoe to polish. Next rectangle, put polish on brush. Next, polish one shoe. Then you loop back to repeat for the other shoe. And finally, an arrow drops down to the stop oval. It takes a normal physical chore and turns it into a perfectly logical algorithm. Pretty cool, right?
But why bother drawing this all out? Well, because they are incredible tools. Flowcharts are super easy to make, and they make even the most complex logic really easy to understand at just a glance. Most importantly, though, they help you spot your mistakes. If you forgot a step in your plan, you're going to see that gap in your map immediately. In the computer world, finding and fixing those errors is called debugging, and having a flowchart makes debugging an absolute breeze.
So, here is the main takeaway for today. Computational thinking isn't just for coding video games or building robots. It's an entire mindset. By breaking problems down, spotting the patterns, ignoring the extra noise, and designing a step-by-step algorithm, you can literally tackle anything school or life throws at you. So I'm going to leave you with this. Now that you have this genius problem-solving blueprint in your back pocket, what massive challenge are you going to conquer next? Thanks so much for joining me in this explainer, and hey, happy problem solving!